Good afternoon, everyone. This is the mission science briefing for the Magnetospheric Multiscale mission, or MMS. And we'd like to show you something first before we go to our briefers. Earlier this morning, at about 5 after 10, we rolled out the Atlas V rocket from the vertical integration facility at Launch Complex 41 out to the launch pad. We see the 53rd Atlas V to be launched. This is NASA's 12th. And once the Atlas V lifts off tomorrow night, it's a fairly lengthy flight in comparison to some others. It'll be an hour and 47 minutes and 12 seconds until the last MMS spacecraft deploys. Right now, we'd like to begin talking about our mission that's coming up, starting first with Jeff Newmark, the interim director for the Heliophysics Division at NASA headquarters in Washington. Jim Birch, the principal investigator for the MMS Instrument Suite Science team from the Southwest Research Institute in San Antonio. Roy Torbert, the MMS Fields Investigation Lead from the University of New Hampshire at Durham, New Hampshire. Greg Pollack, the lead co-investigator for the MMS Fast Plasma investigation from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And Paul Kasich, the associate professor from West Virginia University at Morgantown, West Virginia. And we'll begin first with Jeff Newmark. Jeff?
Thank you, George. Good afternoon, everyone. I'm really pleased to be here today to talk about Magnetospheric Multiscale, or MMS. This is a lot of complex words you're hearing these days: magnetosphere, multiscale, magnetic reconnection, heliophysics. I hope that over this briefing, the next few minutes, we can simplify this, kind of introduce you to the subject and why we're really so excited here at NASA about this. Let's start off with heliophysics. What is heliophysics? Heliophysics is the study of the sun and its interaction with the Earth and the solar system, including what we call space weather. What is this going to do for us? Well, we're looking to answer big questions like, why does the sun vary? How does the space environment around the planets react? And what are the impacts on humanity and our technological society? All of these are what we study in heliophysics. In fact, the Earth and all the other planets are embedded in the extended atmosphere of the sun. We're actually, these charged particles stream from the sun all the time, and we live within this environment. And this environment connects us. We're actually a single system. That's what heliophysics is about. It's studying the connected system from the sun to our space environment around us, to the edges of what we call the heliosphere, this bubble around the entire solar system. When we just to really understand this, I'd like to take you on a journey of space weather, a journey that starts in the interior of the sun, and the motions in there generate an immense magnetic field. This magnetic field then gets wrapped around itself, and the sun, as the sun rotates. And let's see what happens when that, on my first video here, we're looking at is the sun, in the outer atmosphere of the sun. The bright areas are areas where the magnetic field is really concentrated. And you'll see off on the left side of the sun a tremendous explosion, a solar flare, what we call coronal mass ejection, or a solar storm. These storms contain 1 billion tons of material traveling 1 million miles an hour throughout interplanetary space. Occasionally, they come right to the Earth, where fortunately, the Earth has its own magnetic field. And this magnetic field extends into space. We call it the magnetosphere. That's what we'll be studying, the region that MMS will be flying in. It interacts, though, in each of these stages, from the initial flare that we saw at the sun, that is caused by magnetic reconnection. As that giant solar storm gets driven from the sun, that's released by magnetic reconnection. As the storm interacts with the Earth's magnetosphere, that interaction, again, is magnetic reconnection. So this entire journey is a story of space weather, heliophysics, and magnetic reconnection. A really exciting event just happened earlier this morning. There was an X flare on the sun. This is the largest class flare that we classify as stars. And this same kind of series of events, this was on the front-facing side of the sun, and this same series of events is actually going to be unfolding in front of our eyes over the next few days. So we're really excited. How does heliophysics study these events? Well, if you'll see in my next slide, heliophysics, we actually have a fleet of missions we call the Heliophysics System Observatory. We actually have 18 missions with 29 spacecraft throughout interplanetary space, some around Earth orbit, some going towards closer to the sun, some going around to the far side of the sun. And we study all this whole link system that I was just talking about, from the interior of the sun through the release of the magnetic reconnection, the flare of the sun, watching the material stream throughout interplanetary space. We can actually see it today through our stereo spacecraft, impacting then the Earth's magnetosphere. And that's where MMS comes in. The part that's been missing, I've mentioned magnetic reconnection, but we don't understand the physics. We don't understand the details. It's a word, but the actual details we really don't know yet. And that's what we're going to learn. MMS is really going to teach us that. So my last video, I want to introduce you just to the mission itself a little bit. We see the solar storm, like the one that's coming our way now from the sun. This impacts the Earth's magnetosphere. MMS will have 4 spacecraft. You'll hear much more about these spacecraft traveling around the Earth through the magnetosphere, this region, sampling the magnetic reconnection itself, using our magnetosphere as a laboratory, an actual laboratory in space that we didn't have to build. Nature built it for us. And so to learn on how each one of these stages of magnetic reconnection occur. So we're really thrilled to see this launch tomorrow, and hope you can follow us on this journey. And to give you some of the details about the science, I'd like to pass it over to Jim Birch.
Thank you, Jeff. It's very difficult for me to appreciate how excited we all are about the launch of MMS. We've worked 10 years with a large science and engineering team working with us at Southwest Research Institute at University of New Hampshire, UCLA, Applied Physics Lab, and a large science and instrument and engineering team at Goddard Space Flight Center. And all of these individuals work together very well. We're all very happy. We'd do it again in a minute. Now, what's the mission about? As Jeff said, it's about magnetic fields. Throughout the universe, magnetic fields are continuously being generated and destroyed. Now, the generation part is not completely understood, but we have a better idea of what's happening. This is caused by a dynamo effect, where if you have a conducting fluid or a conducting gas that starts in motion with a rotating body like a star or sun or planet, then you can create magnetic fields. The destruction part is more difficult. We know that it's caused by magnetic reconnection, where 2 magnetic fields in adjacent regions, or even a magnetic field in a loop-type configuration, which I'll show in the same region at the base, can reconnect and destroy magnetic field energy. We know it happens. We know it converts that energy to high-energy charged particles and heat. We just don't know what causes it to happen, because these processes happen at the smallest scale of the plasma, which is the electron scale, and any previous mission has fallen short by a factor of 100 of investigating that scale. So this is why MMS was given such a high priority for by the National Academy about 12 years ago, and this is why NASA picked up on that and implemented the mission. Now, I mentioned how this happens. We want to know more, but how does it affect us? Jeff mentioned that as well. Reconnection is the engine that drives space weather. So what is space weather? You have these flares, you have energetic particles from the sun, you have the auroras, magnetic storms. All of these things, every single one of them are driven by reconnection. So we're not setting out here to solve space weather. We're setting out to learn the fundamental features of magnetic reconnection, because that's what drives space weather. Someone else can take that and use it for predictions if they want. Now, reconnection also happens in the laboratory. There are people for 20 years or more who've been trying to harness nuclear fusion by trapping particles in a donut-shaped magnetic field and heating these up to something like 100 million degrees when the fusion starts happening. If you could maintain that, we will have solved the energy crisis. Trouble is, it always crashes. These temperatures always come down repeatedly, and on a plot it looks like the blades of a saw. This is called a sawtooth crash, caused by magnetic reconnection. So we looked closely with the people, like that nice long chat with some of the people from Princeton Plasma Physics Laboratory yesterday after our mission briefing that are very interested in working with us. So there are practical applications once you understand how magnetic reconnection works. Now I mentioned this loop type reconnection where you have a dynamo, say on the surface of a star or maybe in a disk that surrounds black holes, and it creates a magnetic loop. As this expands, the base of that loop might converge. So the outer magnetic field is pointing outward on one side and inward on the other side. They're in opposite directions. That's what you need for magnetic reconnection. So now we look at a video, we're going to see this in the accretion disk around a black hole after a brief introduction about the Earth, etc. But the next thing you're going to see is a black hole, Sagittarius, center of our galaxy. There's the flares, a loop-type reconnection. There's a flare on the sun, exactly the same process. If you look closely, you can see these loops that reconnect at their bases. Now, as Jeff mentioned, when these events become very energetic, they cause outbursts called coronal mass ejections that propagate rapidly towards the Earth. You see here, causes magnetic storms and the aurora, and this is the thing that transmits space weather. But what drives it is reconnection. So there's reconnection on the day side when the cloud first hits the magnetosphere. Not that much happens. When it gets interesting is on the night side. You see in a moment on the right side of this where you have reconnection in the tail of the magnetosphere, and this is what produces the aurora and the currents that carry the energy in magnetic storms. Now, here we're looking in the next sequence here. This is a Bastille Day storm back in 2001. This is another spacecraft that a lot of our same group did, and that was a shock wave hitting the Earth, causing this bright auroral display. Now, how does reconnection work? Well, how do we think it works? We're going to look at a still drawing here. Okay, in one sense, it's very simple, and in another sense, it's very complicated and also mysterious. Simple part is that if you have magnetic fields pointing in opposite directions, let's say the top of this graph of this figure pointing to the left, at the bottom pointing to the right, and if something is squeezing these together, and these are plasmas, one side could be the solar wind, the other side could be a stellar wind, or it could be a magnetospheric flow, but if you're squeezing these together, then we do know that the magnetic fields interconnect, and you see those jets. Those are high energy particles that are produced as you destroy magnetic energy and convert it to particle energy. So we know what goes on around that blue box called diffusion region from previous missions and from theoretical work, but previous missions and theoretical work have told us nothing about what goes on in that diffusion region, and that's what MMS is going to do. Okay, now in a minute, this comes up pretty quickly, so I'll just tell you, there's one of these boxes shown on the day side of the magnetosphere and one on the night side of the magnetosphere, and then right away we come up with a computer simulation showing what the theory says is going on inside those boxes. So you can start that video. See those two boxes, day side and night side, and then you see this is what's going on inside the boxes. You can plot different things. This particular plot is electron currents produced by one of the top computer simulations of reconnection that we have. But these are only approximations because, as most of us know, the protons are about 2,000 times heavier than the electrons. Any of the computers that exist cannot handle that ratio. These ratios are at 100 at best. So these are guides. The true answer is going to come from MMS. Now there's another video that's going to show how we access these two regions of interest, those two boxes. We launch on the night side with that red orbit. It precesses around. You see the sun off to the left, skims the boundary between the solar wind and the magnetosphere. All the time we're adjusting the separation between these four spacecraft. They're in a pyramid formation, but we can adjust it. Second time around, we pick the optimum separation based on the data from the first time around. Then we double our apogee out to 25 RE to access that box in the tail. And there we can adjust the separation from 10 kilometers out to 400 kilometers. The reason we pick 10 kilometers or 6 miles is that's a characteristic scale length of the electrons, especially on the day side where the densities are high. And previous missions have only gone to a few hundred kilometers. So you need to get down to that. You need 4 spacecraft because it's a 3-dimensional phenomenon. As you know, 3 points to find a plane, and so you couldn't do anything with 3. And so this is our strategy. Now the next video here is coming up. Going to show what happens while we're in those orbits. So I mentioned these pyramids, or also tetrahedrons, another word for it. In a minute, it'll zoom in a little bit and they'll separate, and you'll see this pyramid formation. And that pyramid develops and is maintained out in the outer reaches of the magnetosphere. Those 2 boxes we looked at, day side and night side, are at fairly large distances. You can't really tell it that well from this video, but there's the pyramid. And then when it gets close to the Earth, they line up in a line, and when we get farther away, they maintain the pyramid again. And this is done using a very sensitive and accurate GPS receiver and a lot of propulsion. We have propulsion that we can use it once or twice in orbit to maintain almost perfect pyramids in the regions that we're interested in. So now, again, while we're doing this magnetic reconnection is what drives space weather. See this event that Jeff's talking about? Coming this way is going to cause space weather, but it was produced by magnetic reconnection. And when it hits the Earth, its effects are going to be produced by magnetic reconnection. So that's why we're so excited and very excited about our mission. Now I'll turn it over to Roy.
Good afternoon. As Jim mentioned, magnetic reconnection is the process that releases magnetic field energy. And so it's very important on MMS to measure these electromagnetic fields very, very accurately. So starting about 3 days after launch, MMS will start to release a set of booms that have very sensitive instruments on them. We get them as far away from the spacecraft as possible because the spacecraft itself produces electromagnetic fields. If you saw the mission briefing, you know that the mission spent a lot of time trying to reduce the magnetic and electric signature of the spacecraft so that we don't measure our spacecraft itself. So in the first video, we show the deployment of these booms. This is the magnetic booms that are deployed on about the 3rd day. There are 2 magnetometers on the end of 5-meter booms and another magnetometer about halfway in, measuring the magnetic fields very sensitively. And then we just deploy what we call the spin plane double probes. These go out 60 meters each one. There are 4 of them, so that in the end, MMS looks about the size of a football field. And finally, we have the axial probe, which is a unique element of MMS, to measure the full 3D or 3-dimensional electric field on MMS. Now, to give you an idea of the sensitivity, the magnetometers are accurate on MMS to 1/10 of a nanotesla. That's about 1/millionth of the Earth's field. And the Earth's field is actually not very strong. It's about a 1,000th of your typical refrigerator magnet. And the electric antennas are accurate to 1 volt per kilometer. A typical electric field you have is about 100 volts per millimeter, like in your extension cord. So this is a factor of 100 million better than that on those instruments. In the next still, you can see one of those axial probes. A lot of development went into this unique contribution. That's an engineer from the University of Colorado. And you see the spiral nature of that boom. It's constructed so that as the spacecraft spins, the signature or the capture of sunlight on those booms stays exactly the same so that the photo emission from the surfaces does not change as the spacecraft spins. So to illustrate the importance of these fields to the process of reconnection, we have a little simplified lab distribution here, lab demonstration that we'd like to show you. Now the equations that cover electromagnetic fields are called Maxwell's equations. And Maxwell's equations will tell us how this demonstration has many similarities to reconnection, also important differences, and so we'll talk about that too. So what we're going to see in this wire is I'm going to pass a current down this wire, and this will happen in a minute. And when I do that, there will start to be a dissipation in this wire. What Maxwell's equations tell us is, in fact, the current sets up in a magnetic field structure outside this wire, and the electric field in the wire flows the magnetic field in energy into this wire to cause dissipation. Now I can start to smell the wire, and soon you'll start to see it heat. Okay, and that's what we're doing. We're converting magnetic field energy into electrical energy or heat. Now, it's the case that if I crank up the current large enough in this particular constraint demonstration, soon you'll start to see the effects of this, and then very soon we will have an explosion that's very much like reconnection. We released, in this case, the energy of the tension in this wire, but it's those, you saw that hot spot where we have concentrated dissipation, and that's what we're looking for in MMS. We're trying to find those hot spots out in space. Now, you can't see them like we could in this wire because it's a rarefied plasma, and that's the major difference between this demonstration and the case of looking for reconnection in plasmas. It's quite a bit of difference in the sense that in this wire, I understand what happens, why this wire heats up and we cause this dissipation. As it gets hotter, since the wire is under tension, it thins, the resistance goes up, but the current has stayed the same because I adjusted this power supply that way. And so what happens eventually is all the dissipation goes into a very small region, and then it separates the wire. MMS is investigating reconnection because we do not understand at all what causes the dissipation in plasmas. In fact, if you look at current theory, it should say it should never happen because a plasma is very much almost a superconductor, not quite, a very good conductor. And it should never have dissipation like we saw in this demonstration. It would be like all of a sudden all your high tension lines exploded for a reason that you didn't even know, because they should be good conductors. They should take the energy from the power plant to your home, but all of a sudden they don't. So what we seek to find in MMS is to find those hot spots. And if we can get our 4 spacecraft with those sensitive instruments around those hot spots, then we can understand what the electromagnetic fields are doing and telling us about that dissipation. And the other remarkable thing about reconnection is that this dissipation is in heat or disorganized energy. In fact, it's remarkable in reconnection that you get organized energy, organized plasma flows. And Dr. Pollock's instruments will measure those plasma flows via the fast plasma instrument. And those plasma flows are almost at what is the effective light speed in a plasma, called the Alfvén speed. And to know that speed, we have to find the composition. We do that via an instrument called the hot plasma composition analyzer. It tells us how much oxygen, helium, and hydrogen there are in these regions. And then the other remarkable thing is there's a lot of energetic electrons, some of which you saw create aurora in those storms. That's remarkable how much of that energy goes into those energetic particles. And we have the energetic particle detector to measure those particles. So with that, I'll turn it to Craig to tell us more about those instruments.
Thank you, Roy. It's a great demonstration. I'm, as Roy said, the leader of the fast plasma investigation, which involves a lot of hardware. And that's what I'd like to talk about here is really the volume of hardware we have in this mission, in these experiments. It's really unprecedented. And I want to try to give you a sense for why we have so much hardware and show you a few graphics and one interesting video that shows sort of a frenetic activity in assembling some of the hardware. So if I could have the first graphic, please. You've seen this graphic before. What you're looking at here is a simplified diagram of the Earth's magnetosphere. The sun is off to the left, and the Earth is there obviously as the source of the Earth's magnetic field. And then there are the 2 boxes that Dr. Birch pointed out. One on the sunward side in what we call the magnetopause, the other on the tailward side in the geomagnetic tail. These are the locations where magnetic reconnection is expected to happen. And these are the targets, what we call the regions of interest for our flight mission. Now, one thing to remember, the location of the magnetopause at that box on the sunward side, that's not at a fixed location. It moves. The solar wind, which is always blowing past the Earth at very, very high speeds, approximately 250 miles per second, is not a steady wind. It's a gusty, dynamic wind. It buffets the Earth. And therefore, in response to that dynamic pressure, the magnetopause moves back and forth very rapidly. At the magnetopause, the boundary between the Earth's magnetic field and the interplanetary magnetic field, moves back and forth with typical speeds of 50 to 100 kilometers per second. So we're looking for a very fast-moving target. Right now, if I could have the next chart, please. So in this chart, you see sort of it's a sequential zoom in, if you will. On the far right, again, is on similar scale to the previous chart, a diagram of the Earth's magnetosphere. Earth is at the extreme right, kind of colored orange there. And you see a little blue box, roughly the same scale that I showed you in the last chart. But then if you zoom into that blue box a little bit, and you see a region, a more localized region of the magnetopause. I don't know if you can read the scale sizes at the bottom of the figures. On the far right panel, it's about 100,000 kilometers, which is about 60, 70,000 miles. In the center panel, we've zoomed down to where the width is about 500 kilometers or 300 miles or so. And then finally, we zoom in again to the area that contains what Jim referred to as the electron diffusion region, and that box is only about 100 kilometers across, right? And the place where the action all occurs within the diffusion region is only about 10 kilometers or 6 miles across. So you got this little feature, 6 miles across, moving past you at 50 miles per second, right? And you got to capture the details with 4 spacecraft inside that feature in order to understand what's going on. 4 spacecraft gives you the 3D, but on each spacecraft, we need to make our measurements very, very rapidly in order to capture the feature as it moves past us. So if I could have the next chart, please. So what you see here are some of the elements of one of the instruments, one of the sensors in the fast plasma investigation. In the center of the figure, you see what looks like kind of a 2-headed box. That's a dual electron spectrometer, which is one of the 2 core instruments for the fast plasma investigation. The dual electron spectrometer has 2 sensor heads, therefore the word dual, and it measures the fluxes of electrons and ions, fluxes of electrons at a very rapid pace. But not rapid enough by itself, that one box, in order to capture the features we need to capture as rapidly as we need to capture them. So our approach to that, typically the MMS spacecraft will spin, and they'll spin 3 RPM, 3 rotations per minute, right, about a 20-second spin period. That's far too long to wait to have your instrument spin around and get a view of all space. So our approach has been to proliferate many instruments around the perimeter. So we've built 16 of those dual electron spectrometers to measure the electron flows and fluxes, and 16 dual ion spectrometers, which will measure very similar instruments but not identical, and they'll measure the ion fluxes. If you'd go to the next chart, please. So here's the first 4 dual electron spectrometers that rolled off the line. I call it a line, but not really an assembly line. They each take a lot of tender, loving care. That's myself on the left, and our chief engineer on the project, a guy by the name of Ulrich Glees, on your right. And that was roughly December 2012 when we had those first 4 complete instruments on the clean bench. Now, I've described briefly, that there's so many elements of the fast plasma investigation. It's also true of the fields experiments. The boom deployments that Roy just described, 4 extending 60-meter booms on each of the 4 spacecraft. That's 16 units to get together. 16 of those axial booms, which extend 30 meters out either direction. Just a whole lot of hardware has gone into this, and that's one of the reasons why it's taken us this many years to get to this point where we're ready to actually fly it. If I could have the next chart, please. So here's another stage of quite an advanced stage in the development of the mission. What you see in this picture, there are 2 MMS spacecraft in the picture. In the back of the room there, you see a giant vacuum chamber. That's a thermal vacuum chamber where we test, we put the entire spacecraft in there. You can see the kind of black-colored solar panels. And we run it through about a 2-week test, cycling temperature up and down to ensure that the spacecraft can endure the temperature variations and rigors that it will encounter while it's in flight. And then to the right, you can see another spacecraft. It's got the covers on the solar panels so they don't appear black, red covers on the instrument apertures, and that one's waiting in the wings. It'll be the next one to go into the thermal vacuum chamber. So all 4 spacecraft were run through this thermal vacuum sequence very successfully and very efficiently. Next chart, please. So in this chart, this is in a clean room up at Goddard Space Flight Center. Again, a very advanced stage. You can see all 4 spacecraft, all with their solar panel protective covers on, sitting distributed around the floor of the clean room on platforms. And that's just before a really important stage, which is the stage where they all get stacked up in a stack of 4, which is exactly their launch configuration, in order to vibrate them and shake them real hard to ensure that they can withstand the vibratory rigors of the powered launch phase. So what I'd like to do here is, and I won't speak much through it, but I'll show you a time-lapse video. It's 3 days compressed to 1 minute of the assembly of those 4 spacecraft into the 4-stack launch configuration. And of course, this all happens in a clean room, uncomfortable, working all day in those clean garbs with usually masks over your face and everything covered, but it's necessary in order to keep the cleanliness of the spacecraft that we require. Many of these instruments are highly contamination sensitive. So when I said frenetic activity, this video is the one that I was referring to. This activity was filmed using the GoPro cameras. They had to be moved occasionally in order to catch the right views, which was non-trivial. A lot of work over a period of years, a lot of work just over those 3 days, right? And so now, if you show the next chart, please, which I believe is my final chart. There is the 4-stack of MMS spacecraft. To the left and right, you can see the 2 halves of the Atlas shroud. So this is immediately before encapsulation into the shroud, just a couple of weeks ago now. And that has now happened. The shroud has been mounted on the top of the rocket, and the rocket moved out to the pad. And we're just absolutely thrilled to be at this stage after a lot of really hard work on the part of a whole lot of people. And having described that stuff, I'd like to turn it over to Paul, and he'll tell you a little more about the science.
Thank you, Craig. So, yeah, I'm a scientist that studies magnetic reconnection, one of maybe a few thousand in the world that study this process. And, we're at universities, national labs across the world. And there's a group of them just down the road that are having last-minute meetings. And I got to tell you, the place is abuzz. Everyone is just really excited for this day, for tomorrow. And so, what's so exciting about MMS for us is that we're going to be able to see the region of reconnection where the magnetic field lines break. And that's something we've never been able to see before. And so it's just really exciting. The folks to the right have just done a fantastic job of getting this all ready, basically building a lab and sending a lab through space. So everyone's really excited about it. What I wanted to do is kind of take you through some of the science that we've heard a little bit about, but I want to go through a little more detail and maybe some detail about Roy's demonstration here. So when we hear about magnetic reconnection, it doesn't seem like something we can really grasp. So I want to show you that it's actually something that you have at least some experience with if you've ever played with magnets. So here's 2 magnets. This one's shaped like the Earth, but there's a magnet inside. So we all know from playing with magnets that if you bring them together and they're both oriented the same direction, they push apart. And if you flip them one upside down, then they attract. And so what's going on here is that you have magnetic fields coming out and around on both of these. And so if they're pointed the same direction, you squeeze those magnetic fields together and they basically push back, and that's why you can't push the magnet together. But when you flip them and one's opposite to the other, the magnetic fields point in opposite directions, right? And what happens is if they're pointing opposite directions, they join, they break, and they shoot out the top and the bottom. And that's what allows, since there's less magnetic fields in between, that allows them to come together, and that's what you feel is the attraction. So magnetic fields breaking is actually something that is at least somewhat familiar to us. What's different about magnetic reconnection in space is that rather than this room where it's just made up of air, in space it's made up of a plasma. And a plasma is a really hot gas, and hot gases like plasmas respond to magnetic fields. So if in this room, if we had a plasma instead of air, as we bring these magnets together and they come together, the magnetic fields would break. And as we saw in some of the images, you would get a jet of plasma going up and down, just shooting out the sides. You'd get a spark, kind of like what Roy showed in his demonstration. Okay, so those two things together basically give you magnetic reconnection. So what I want to do next is show you an animation of how that works in space in the near-Earth environment. So if we can bring up this image. In the middle is represents the Earth, and those big yellow lines represent magnetic field lines. So you can see a number of them go from the top of the Earth to the bottom. Those are the ones within the magnetosphere. On the left, you see one that's kind of open. It doesn't connect to the Earth. So this one is getting blown in by the sun, by the solar wind, and it's pointed in an opposite direction to the Earth's magnetic field. And so what's going to happen when it moves to the right is that that magnetic field is going to break, and that's magnetic reconnection. So let's go ahead and roll the movie, and you can see it come in and break. And that's, again, the magnetic reconnection process. And you see it doesn't stop there. That was the day side one. But now those magnetic field lines get dragged away from the sun to the magneto tail, and they're again oppositely directed, and those break, and it can shoot particles back towards the Earth. And we've heard that magnetic reconnection plays a strong part of space weather. So it's shooting those particles back towards Earth that can cause the problems with space weather, like satellites or communication problems, things like that. The other thing you can see from that animation is that you have things happening on very different scales, and that's why the MMS mission is called MMS, Magnetospheric Multiscale. So multiscale refers to the idea that you have something happening at a very small region of space where the magnetic field lines break, and it affects what's going on in a very large region of space. So as we've heard, the entire reconnection process happens only over 6 miles, 10 kilometers, and the whole magnetosphere is about 1 million miles. So something that happens in a very small place affects the large scale. And as we've heard, we have instruments up there that measure the large scale, and what we've never had is an instrument to measure the very smallest scale. So that's what MMS is going to be doing for us, is measuring those smallest scales. Another thing I wanted to share with you is we've talked about solar flares, and that reconnection happens in the sun and many other places in the universe. It can happen in fusion devices. It happens at the edge of the solar system where it runs into interstellar space. It can happen at compact objects like neutron stars and black holes, these kinds of things. So I wanted to show you an example of reconnection happening in the sun. So if we can bring up the next image, what we're looking at here is an image from the NASA SDO satellite, the Solar Dynamics Observatory. This is what the sun would look like if we could see in the ultraviolet range. And what we see here is a number of loops on the edges of the sun. What that is a number of charged particles. They are giving off light, and so we see that light in the ultraviolet. But those particles are trapped to move along magnetic field lines. So what that's really giving us information about is the magnetic fields themselves. And so what you're going to see in just a second is the telltale signs of reconnection. Right in the middle, you'll see material moving towards the center, and then you'll see it get shot up the top and the bottom, just like if we were bringing these magnets together and the magnetic fields go to the top and bottom. So let's go ahead and roll the movie. So you can see the arrows are pointing to where the material's coming together, and then you can see it getting shot out the top and the bottom. So that shows very directly that magnetic reconnection is happening in the sun. And what's interesting here is you can use another satellite mission called the RESI satellite, which measures X-rays, so even hotter material. So you can see the orange blobs here. Let me tell you what that means. What we were looking at initially was about 18 million degrees. And the RESI satellite looks at X-rays, so it's much higher energies. It's about 200 million degrees. So what RESI tells us is where the most energetic particles are. And what we saw with those blobs is that those blobs were telling us that right near where reconnection happens, that's where the most energetic particles are. And so that tells us that reconnection in the sun, in the atmosphere of the sun, is producing those highly energetic particles. And so with MMS, we can't directly measure what's going on in the sun. We can't stick a probe right there, but we can stick a probe in the Earth's magnetosphere, and we can measure how particles are accelerated by reconnection in the magnetosphere. So by learning that, we'll be able to understand what happens in the sun during solar flares. So just to give you a feel for how much energy is released, we saw in Roy's demo a nice spark. Cosmically speaking, that wasn't a huge amount of energy. When we're talking about solar flares, the largest solar flares give off absolutely huge amounts of energy, and that's all because of the reconnection process. So some of the largest solar flares give off the same amount of energy. Basically, it would take about 40 billion atomic explosions to give you the same amount of energy that is given off in a very large solar flare. And solar flares happen over the scale of about 20 minutes. So just insane amount of energy, the most energetic events in the solar system. And so that's why learning about reconnection in the magnetosphere is going to help us understand reconnection in these other places. So in summary, MMS is just fantastically exciting for scientists studying this, because we're finally going to get to see what happens right where the magnetic fields break. We're going to be able to measure how the charged particles gain energy, and it's really going to give us a lot of perspective on how reconnection happens all over the universe. So with that, I'll pass it back to George.
All right, thank you, Paul. We're ready now to take questions. And when you get the microphone, if you would give us your name and also your affiliation if you have one. Questions out here in the front?
Hi, Ken Kramer for American Space and Universe Today. Can you talk about these hotspots? How will you be maneuvering these spacecraft to search for the hotspots and collect the data?
Well, I'll take that question. As Jim mentioned, we maneuver them into a pyramid shape to get a three-dimensional view. And then we've constructed the mission profile, as I said, in these two phases to go to where we know from previous missions it must be occurring. And then, as Craig said, these hotspots move back and forth, and basically we sit there and wait until they come by us. But we know from previous missions that the probability of us encountering them is very, very high. We expect to encounter a few hundred of these mission hotspots that we know we can isolate what's really going on, and that's what we'll use the information that's captured in a very small amount of time. I don't know if Jim mentioned that the information from all these instruments is so large that we can't actually get it all to the ground. We can only end up getting about 2% of the real information down to the ground, because there's so many instruments and so much data occurring in that very small time. It's a sub-second that we have to get. And so what we do is we have a process to look at indicators on the ground and say, this is the data we want. And we'll have an argument about whether that data is what we really want, and we'll send some of it down, and we will keep doing that until we find what we really need to isolate the physics of reconnection.
If I could add, what Roy just described, we do have a process where we, essentially when we're in the region of interest where we may encounter reconnection, we send down a low-resolution data set. We call it the fast survey data. And on literally a daily basis, scientists will review the low resolution and pick 2 minutes here, 30 seconds there, 30 seconds there. We get about 15 minutes a day that we can budget like that. And so there's scientists inspecting the low resolution data while the higher resolution data is stored in memory on the spacecraft. We'll select these little intervals based on inspection of the low resolution flight data to send down the full resolution data from which we hope to glean the details and understanding of the process.
I'd like to add, you asked an excellent question. You're going to see it takes three of us to answer it. We can't drive these spacecraft through that region of interest. You have to establish the pyramid on an orbit-to-orbit basis. So we get what we think is good, we go through. Now, Roy and Craig mentioned what we call a scientist in the loop, where scientists on the ground look at low-resolution data and say, here's a good boundary, we think this is good. But what are they comparing that to? We also have a system on board the spacecraft that can look not at the low-resolution data, but can look at the burst mode, the highest resolution data that we can take. That system on board with software is selecting regions. So what these people on the ground is doing is really deciding, do we need to trump what the onboard system is decided to send down to us? And for this, we needed a very large memory, radiation hard, about 100 gigabytes, 96 gigabyte memory. And we constructed this out of, you're familiar with these flash drives in your laptop, because it was too expensive to buy one at those specs. And so we had a clever engineer that said, you know, some of these flash drives might be radiation hard. We don't know. So he bought a bunch of them up, took them to an accelerator in France, and found out some were really hard, some lots. And so we bought up all of that stuff, and that's what's on there. And we're also turned into a line of business. We're selling those memories to other folks now.
Yep, right back here.
Historical Imagery, Mark Gotch, Canada. An amazing presentation you've given this afternoon to look at the amazing amounts of hardware that are going to be installed in these satellites and working. Sending this information back is just incredible. But to ask you a question, when these satellites will be orbiting Earth and recording these magnetospheres, in reverse, from Earth, how far out into space will these magnetospheres being monitored in terms of capturing the information with this hardware? How far out into space from Earth will it be?
What we showed there, or what I showed in that animation of the orbits, the largest distance we go to is 25 Earth radii. Each Earth radii is about 6,000 kilometers, 6,300. So, you know, it's like halfway to the moon. That's as far out as we go. Beyond that, reconnection happens only rarely. It still happens. But we know from previous missions, statistically, where it most likely happens. On the night side, it's halfway to the moon. And on the day side, it's a quarter way to the moon.
Right here.
Ed Ruskowski, social media. How long do you plan to take measurements with your vehicles? And also, what is the planned mission life?
It's a 2-year mission. And we won't be out of fuel, though. We'll still have fuel left. And so if spacecraft are healthy, we would probably propose to keep running it for a while. But as of now, 2-year mission, an additional year of analysis of the data.
Right here.
Hi, I'm Yolanda Kearney. I'm the Public Affairs Officer at U.S. Embassy Bridgetown, where I'm lucky I have an ambassador who's a former physics professor, so thank you for making it all look easy. So around the world at our embassies, we still have people who draw a tremendous amount of inspiration from NASA. We were lucky enough to host Neil deGrasse Tyson for a lecture in November. A little 6-year-old came up to him and asked him, what if there were no NASA? So he gave a beautiful response. But I'd like to know what your message is for us around the world as we talk about the influence of NASA still. What if there were no NASA? That's for Jim or Roy, or whoever wants to take it.
You asking me?
Yes.
That's a good question as well. Well, you know, I still remember when there was no NASA. Yeah, I've been at this game a long time. And so, you know, and then there was a NACA. It was mostly an aeronautics thing. And so what got people interested was the space race. Of course, the Russians put a Sputnik up, and well, we had to get a satellite up, and then they put a man in orbit. Well, we had to do that. It was mostly like that. But as time went by, there was a very excellent science program developed in NASA. It's like a National Science Foundation embedded in NASA. And everything is done, it's a meritocracy, everything is competed every mission we do, like this one, was heavy competition to pick the people who do it, and so nothing is just given to anybody. So people are very interested in the space science and are willing to go to school and learn more about it and compete with other people to get to do these missions. If NASA ceased to exist, I think what we know about space, about the universe, really would just cease. We wouldn't know anymore. That's it. I mean, it used to be close to the Earth. There's the Navy and the Air Force fly some satellites, but all that kind of stuff we mostly know about. But farther out, we wouldn't know. We'd be looking to the Europeans, the Japanese, the Indians, the Chinese. We'd be reading their journals instead of ours. Sorry, Jim.
No problem. I think I'll add, and sorry, Jim, I don't remember a time before NASA. I think that NASA provides a fundamental impetus for science in this country. I think that it's a partnership. You see a representative here. I work for NASA, Jim for a company, Roy for university. So you see the difference. I think NASA provides a force that helps unify and provide inspiration to the nation to do this great science. So I think that at the time that what would happen without NASA, I think you'd lose something. You rely. The individuals are spread throughout. They're at the universities. They're at the corporate world. But I think that the NASA's role is really to lead, help lead people into a common direction that will really benefit the whole nation in unsuspecting ways. We really don't know. As you heard here today, we're really interested in the fundamental physics of magnetic reconnection and then how it relates to activity in space. But yet there may be an offshoot of understanding about fusion reactors here on the ground. Throughout NASA's history, there has always been that dual nature of pure science and yet practical application. So I think that's, I would say, the role.
If I could respond, just because I teach undergraduates on a regular basis and graduate students too occasionally, but I can just say very simply, NASA provides really that spark for imagination, which is really important for education.
Any further questions?
May I add?
Yes,
please?
certainly.
Just an hour or two ago, I was lucky enough to visit the Apollo Saturn V Center here on Kennedy Space Center. And I took the occasion to see this 14-minute video show that they have about the moon landings. And through that video and at the end of it, there were some interviews with astronauts. And Alan Shepard, I believe it was Alan Shepard, related his experience standing on the moon, looking back at the Earth, and contemplating how unfortunate it is that back there on that small lifeboat in space, people are busy fighting each other in conflict. And he said he actually shed tears. And I think that one of the important functions of NASA really is to give ourselves an opportunity to see ourselves in a broader context and understand that this is sort of a lifeboat Earth, and to perhaps imagine a little bit better the futility of the conflict that we engage in all too often. And so I think that that's something that NASA has brought to many people's consciousness and will continue to do so in the future. And I think that's a really important role for NASA.
Okay, right here.
Yes, Chris Haber, Haber Digital Media. I was hoping if you guys could go through basically the timeline of the science from back in the 40s when the phenomenon was discovered through some of the previous missions that have worked on it up to the decadal survey that brought us to here, and then milestones throughout the mission.
I think Paul is a good person.
Sure, I'll take that one. Reconnection was discovered in the 40s. It was from people studying solar flares. They realized that where the flares were coming from is where the magnetic fields were pointing in opposite directions, and that's what got people started thinking about that process. Almost immediately, they realized that the same process would happen at the Earth's magnetosphere. So in the the late 40s and early 50s. And so basically by the mid-60s, there were a lot of the theory was sort of worked out, and they kind of thought they understood it. And then but not everyone believed it yet. And so it took into the late 70s when the icy satellites were up, and they measured they weren't measuring the smallest scales of reconnection, but they measured after effects of reconnection, and that's when people really started believing that reconnection was happening. So since then, it's really sort of exploded as a field, and there are a number of satellites. Jeff showed the HSO, the Heliophysics System Observatory. Thank you. And so a lot of those satellites, as they're going around the magnetosphere, they detect reconnection. So so we can see, like we've heard, we can see a lot of what's going on at the large scale, and as you get closer down to the smaller scale. But what's been missing from that is the smallest scale. So that's how MMS fits into that.
Okay, we're going to take a couple of questions from social media, and then we'll come back here.
Calla Cofield with Space.com. I have two questions. First of all, just curious if there'll be any joint observations or, I don't know, cross-referencing, if MMS sees an event looking to see if there's a geomagnetic storm associated with it or auroras or anything like that, if other satellites will be able to see anything to do with these events. And secondly, have you thought about what would happen if MMS got hit with a coronal mass ejection?
Okay, well, I can answer it unless Jeff would like to, but he has this heliophysics system observatory. So all the spacecraft that are already up there, and we'll join that fleet when we get up there. And so all of these spacecraft can see these effects. And so there'll be a lot of work done by researchers in correlating data among different spacecraft, that we have up there. We have designed MMS to withstand these events, coronal mass ejections that you have. But primarily we do it by having a uniform conducting surface on the spacecraft. We have a device on there that emits ions to keep the spacecraft potential from rising above 4 volts positive. And so if it does, the spacecraft could charge up to kilovolts as long as it's uniform. What causes problems with spacecraft is this side's charged one way and it's charged the other way, and you get a lightning bolt across it. That can be a problem. But that's the way you avoid that, is to minimize or eliminate insulators on the outside and have a uniform conducting surface. Maybe Jeff can add.
And I'll just add, we a number of our spacecraft that we have currently flying have utilized these designs where we have had CMEs, solar storms, wash over them, and we do it on purposely so that they can understand them. We can actually measure them. We can see them from a distance with remote sensing instruments, but we also have in situ ones which actually measure the plasma conditions, the composition, the magnetic field. For example, our ACE spacecraft or our SOHO spacecraft, these other spacecraft have already existed. So we know how to design so there won't be any damage. And as Jim said, indeed, it's our fleet working together. It's that system. We have a series of buoys, basically think of buoys throughout interplanetary space, all working together, following this entire series of events. So it is very key to have that understanding.
Okay, questions on Twitter.
I'm going to combine two questions that came in through Twitter through #MagReconTogether. One is, when does the first bit of science data come back into y'all? And the other question is, MMS is a planned 2-year mission with fuel to spare. What else would you want to measure?
Well, I can answer the first one. We're all thrilled. I'm going to see data on Monday. These guys assure me I'm going to see data on Monday.
I don't think I'll see it until about Wednesday.
Yeah, and what else might we look for? Let's say in an extended mission, I think that's what was asked. Well, this mission is designed explicitly to look for one thing and to look for it in great detail. And so any other thing that we find there'll be surprises. We'll measure things that were unanticipated, and then we'll investigate those in more detail.
I'll just add that every mission we launch always comes up with something unexpected. that we just had not participated. We designed it to solve a problem, but something new always comes our way. Something new and exciting. We love new things. We love where it points out that we didn't understand this other process or this related process. I mean, that's how we make advances. So we're just thrilled to see what will happen, see what we don't know.
Okay, another question on Twitter.
And another one that came in through #MagRecon. Jim Birch mentioned using GPS to help guide the spacecraft. How exactly does that work? Is it like my car?
Yes, it is, but you have to have a much more accurate GPS system. We call it the Navigator. We have some project people here who will correct me if I'm wrong, but the GPS satellites are well below MMS. They're at about 4 Earth radii, and we're at 12 to 25, depending on the phase of our orbit. But we can look down into that constellation of GPS spacecraft, and if we make the measurements of their signals accurately enough, we can measure our spacecraft positions down to 100 meters. So we have separations as small as 10 kilometers. We need accuracy of 100 meters, and we can do that with that system.
Okay, you got any more? All right, then we'll take another question right here.
Brian Rue with Social Media. What kind of computing power is going to be used to parse this data as it comes down from the 4 spacecraft? And where might that be located?
You mean on board or at
No, on Earth. On Earth.
Oh, on the Earth.
Mm-hmm.
On the Earth, it's very advanced, and I don't know who here is best qualified to talk about it. Maybe
Well,
Ron.
we have a data center. Each system has a data center. It's coordinated with NASA data centers to ingest the data and to reduce it to a form that we can start talking in a sensible scientific manner about the data. But we also have with the team a theory and modeling component, and the theory and modeling component has these very large simulations that Jim showed. They do that. We constantly compare our measurements to those simulations, and they're run all over actually the world in some of the very largest supercomputers because it takes a very long time. A very lot of computing power to run some of those simulations. As Jim mentioned, they're really limited in their duration simply because the plasma is so complicated that the simulation can only take a piece of it, and we have to go look at the real world and compare that to those simulations. But as I think Paul mentioned, we have a meeting that's going on at this present time this morning of people all over the world who were talking about their simulations and where they're run in various different places, and very anxious to compare it with Mother Nature.
All right, we'll take one last question right here, and then we'll wrap it up.
David Vanderpool, Social Media. Are there other missions, other programs that will be leveraging the data that you gather here? Is there sharing of the data that you gather across your colleagues beyond MMS?
That's an excellent question. There are some existing missions, like the European Cluster Mission, which does a similar thing. It's got, coarser resolution and a lot of things. But I think if we're in the same region of space, we can do a lot with cluster. The other one is Themis. In fact, Themis did some maneuvers about a year ago to put them in alignment with MMS so that we have our spacecraft skimming the dayside magnetopause. Themis at that same time will be exactly 180 degrees out of phase. If we're at noon, they'll be at midnight. And so, we'll look at reconnection at the day side, and they'll look at the effects on the night side, and vice versa as they go around. So their apogee's 12 RE, exactly the same as our day side apogee. And so we look forward to a lot of correlations with them, and they really took the initiative because their spacecraft their mission had been going for something like 7 years. Of course, they're looking for something new to do. They had 5 spacecraft. They sent 2 off to the moon, and they all of a sudden, here we come, and it was really their idea to sync these missions up. And so now we're doing it.
The last part to answer your question is also the data, as soon as it's validated and calibrated, is publicly released. So scientists around the world actually have access to the data. It is not kept to NASA or the MMS team. It is actually distributed for anyone to look at the data, to run their own models, and there are also many people are invited to work with the team on developing models. So it really is an international in that endeavor.
All right, we're out of time, so that's going to wrap up our briefing and a brief programming note. Our NASA TV launch coverage will begin on Thursday night at 8 p.m. Thank you very much.